Well, welcome everybody to this extended webinar on frequency response analysis, and hope you've got your cup of tea or coffee to keep you going. I think in the last webinars I've done a bit too fast, which is why we've decided to slow things down a little bit here and try to explain things a little more, do more teaching than just presenting concepts quickly. So let's see how it goes, and I think the intent is to stop a few times in the middle of this session and take any questions. So if you have any questions to ask as we go through related to frequency response, feel free to ask those, and we'll try to either type the answer, or if it's an important question for everybody, then I will get a little flag from my helpers here, and we will answer that for the whole audience to hear as well. So welcome to everybody. Hundreds of people flooding into the room now. I see some old friends out there who are coming in. So good to see you all again. And the topic today is frequency response masterclass. And I'll tell you why I call it a masterclass in a little bit. But you do have a download that you can collect. If you click on the handouts, you can download the PDF of the presentation here. Now, a lot of the presentation, as in our last webinars, we're going to try and do a lot of live things here. So I think it's more exciting for engineers to see us hook things up and do things wrong, and hopefully not blow anything up, but that's always a possibility as well. So we're going to try to keep it as live as possible. And we thought about setting up lots of frequency response analyzers to have pre-setups here, but that really doesn't give you a feel of what it takes to conduct the measurement. I'm always a bit disappointed when I see something pre-set up and somebody pushes the button. You know, you might as well just look at the simulation at that point. So we're going to go through connecting the cables, and as I say, just at a more relaxed pace this time, to see how this whole process of frequency response analysis works and can work for you. So first thing I'd like to mention the big influences in my career in frequency response. And of course, we can't say anything without mentioning Mr. Bodhi. He was an engineer at AT&T Bell Labs, or it was just Bell Labs back in those days, and very much involved with feedback control and many other topics. He actually came into control a bit later in his career, did many other analytical things before that. And quite honestly, he gave modern engineers, especially power electronics engineers, the greatest possible gift he could with the Bodhi plot, which is plotting, the relative gain of two signals and plotting the phase of the two signals at the same time. And we'll see that why that was such a great gift. Now, the work was done in the 1950s, I believe, was when it all came out. And he actually retired in 1961. But for today's practicing, power supply engineer, power electronics engineer, it is still the tool of choice for getting most of your job done. And for that, we should be enormously grateful that he came up with his techniques. And I'll explain why in a little bit. So next person I want to thank is Dr. David Middlebrook. So I came out of university in 1981, and then in my first job, I took his structured analog design course. Almost immediately, I started work, and that was because the power supply company, or it was a computer company I was working for, knew that they needed to start measuring some loops in their system, and they didn't know how to get things stable. So I took his structured analog design course, and of course, Middlebrook is known for his theory, his circuit theory, his extra element theory, and many analytical things that he did in his life. But when he came to teaching the courses, it was very hands-on, and he was very insistent that measuring the loop was part of the process. And there was always this thought about, well, if you've done so much modeling, so much circuit analysis, why do you measure a loop as well? But of course, he knew that the real world didn't always agree with the theory. And of course, at Caltech at the time, they were very busy building hardware for everybody. And when you build hardware, this comes to the surface very quickly. That there's discrepancies between what you measure and what you predict. So the measurement has to win. And this is still something that is constantly a battle for engineers and students these days. You've got a way of predicting how things will work, and then you have a way of measuring. And when they don't align with each other, what is the proper course of action for you? And of course, when you're in industry, the course of action is you've got to solve the problem as quickly as you can and get the product out the door because you've got deadlines to meet. And then if you're in academia and you've got a separation between the two, you have to work on resolving it because you need to publish it and explain why your new analysis is a little bit different from what you're measuring. But anyway, yeah, Dr. Middlebrook, I went to all his courses. He became a friend later in life, and we had many discussions about all these topics. But if you can dig up some of his old courses on structured analog design, highly recommended. Another funny story is, I just finished and graduated. I was pretty high in my class. I thought I was a pretty good engineers near. And the first day, he gave everybody in the course the problem of biasing and analyzing a single transistor common emitter amplifier. And I, along with everybody else in the course, didn't have the faintest idea of where to start because the problem involved design. You had to design it, you had to make it work. And that was something that really hadn't been taught to us. We'd been taught analysis of something that somebody else had designed. We had to create the design. So I think he was a little surprised at us all that we didn't know how to do a simple common emitter amplifier. But I've learned how to do it since then, so I know how to pass that course now. Oops, sorry, going the other way. Dr. Fredley, I worked for 3 years, after I took the course from Dr. Middlebrook, and then it was all about designing power supplies, and then suddenly it was about designing another power supply, and I felt, well, I've done this before, so time for something new. So I went back to get my master's degree with Dr. Lee down at Virginia Tech. And Fred, again, was great on hands-on. I mean, the main strength of the power electronics labs in Virginia Tech was it was all about practical experience. And I think most of the students that went there would all agree that, maybe we learned about 5% of our schooling from attending classes, lots of lectures from lots of, people, but the real learning was done in the lab. We had 50 or 60 of us would be in the lab till late at night, every night, learning from each other, making measurements, making mistakes, blowing things up, and coming up with new and creative ideas. So that emphasis on labs and measurements and practical building of things is so important in the universities. And I see quite a few of them are adopting more of that these days. But also for any professors out there, I know it's hard creating practical hands-on labs because just the budget to be able to do that, to be able to order parts, to have oscilloscopes for everybody is a challenge. So anyway, Fred, I think he just recently retired again, but he will never be out of power electronics, of course. I know he's still very active. And then we have Dr. Vorpirian. He was one of the, still is, not was, he is one of the best minds in our industry in terms of analytical work. And he was Middlebrook's student, and he followed on Middlebrook's work with more on the extra element theory and just generalized fast circuit analysis. And I don't know anybody better at analyzing circuits than Bache. And if I have a circuit problem to analyze, I don't know how to do KCL and KVL very well anymore. So I pick up the phone and call him and send him my circuit, and he does the analysis for me in a few minutes that would take me a couple of days to do. So those of you in industry who feel bad that you're not doing much circuit analysis anymore, your job doesn't allow you, don't feel bad. You're not alone. And as I use the resources I can to help me with that. Arch is not available, I might ask a student who's more involved in circuit theory to take care of that. And I want to thank Art Nace, who's a retired aerospace engineer, and he's the programmer who does all the LT-SPICE modeling for us and converts all our programs from RidleyWorks into LT-SPICE. And I think he's amongst our longest users of RidleyWorks, used to be Power 456. So he's been using that for over 30 years now. So he's a strong beta tester for us. And then John Beecroft, he's in the room here. John worked for almost as long as I did in industry. He's been in the industry for almost 40 years as well. And he helps us with our courses now. He's a course instructor, and he's actually working with us here at Ridley Engineering. And he's been testing and a proponent of RidleyWorks for over 20 years as well. So both of those engineers there have been hugely helpful to our program. And of course, he helps me with all this teaching as well. So without them, and of course, Denise Ridley is in the room here too. She facilitates all of this and helps me with the teaching setups and so on and organizing. So thanks to everybody there. So there you go. There's the people that are important here. And I encourage you to go read about Bodhi and his past. Go read Dr. Middlebrook's papers. I don't know if his videos are still available. They used to be. You could find those and download those, but we'll make an effort to try and find those again. But there's no shortage of material to read in this industry. All right. It's my pathological fear of Bodhi. Not mine, but it belongs to a lot of people in this industry. And it's been this way for as long as I've been, measuring things and testing things, that there's a segment of the industry that absolutely will not measure a Bodhi plot under any circumstances. You can give them the reasons, you can give them, well, it's easier to do it this way, it works better to do it this way, but no, they're not going to do it. Everything they want to do is time domain. And some people just have their minds organized in time domain, and they just not comfortable with Bodhi plots and all that they mean. And I think part of it also is born from the university, that people come out of university, they've seen the theory, and they've never measured a Bodhi plot. They don't have the equipment, or it's just considered somewhat antiquated to go in and measure Bodhi plots. So I'm not sure exactly what the source of it, but it's very real. And if you find yourself in that category, then maybe, excuse me, I'm just adjusting another screen here. Maybe we can help you get past that fear of it. But where does it come from? Well, it's quite obvious where it comes from. This is what's involved when they gave you Laplace transforms. So the beginning of Laplace transforms was you did Fourier transforms, and then you did integrals from 0 to infinity with a convolution of the function and a sine. And it involved imaginary numbers. And when you went through the math, if you were a mathematician, you had mathematical bent to it, you had to learn the derivation of Laplace transforms in order to be able to use Laplace transforms. And, many of us, it's just not comfortable. You can go through the routine, but you don't feel it. How can you feel an imaginary number? They don't exist. And it's just a mathematical construct. But the teaching, I think, has probably always been this way, is emphasized on, well, how do you derive this? How do you solve problems? How do you write equations? Everything revolving around the Laplace transforms, which is, J omega, and J being the imaginary number, which is hard to get your mind around and use. So great that people doing research need this, but everybody coming back to the engineering world, and you've got to do something real, and you're sitting on the bench, and then you've got to measure something. It's like, well, tell me about that imaginary number again, how that fits into my test equipment here. And of course it doesn't. When you test something, there is no testing with imaginary numbers. There's real signals. They're real time domain signals that you collect and process and average, and then you've got got Bodhi plots. So I think the math that's behind it is a big blockage to people using it. I don't know how many students here. We probably got about 50% students here, and I'm sure you're all looking at these. Oh yes, that's pretty easy. I know how to do that. But when I took 3 years to go to work and then came back to go to university again, the one thing that had gone from my mind was calculus. It just wasn't there, because when you're working and you're building circuits and doing board layouts and making a power supply work, you just don't practice. So that disappears fairly quickly, and yet you get the job done without the math there, because you learn the tools, the practical tools that make it all work. So that's just my theory. This is Wikipedia for Bodhi plots. Doesn't do much talking about the plots. It does a lot of talking about the theory behind the plots. So a very academic slant to it, which isn't particularly helpful to practicing engineers. So I understand the fear. That's certainly a real thing. And if you ask me to solve these equations today, it's like, no, I'm not doing that. I'm just not going to go there. But what is the magic of the Bodhi plot? Well, here's a little circuit, a little LT splice circuit, which is, at its heart, there's a little buck converter here, a switch, a diode, an inductor, and a capacitor. So there's a little buck converter. So that's like a two-state circuit. And of course, in control theory, you did second order circuits all the times and everything was fine. You could do the damping and the Q and the, look at the characteristics of that LC filter all day long, and look at the gains and the PWM switch model, and everything was fine. But it didn't quite deal with the situation that, well, actually it's not really a two-state circuit here. I've got the L and the C, and then I'm doing a bit of current mode here, and I've got another C in the control, another C in here, and then I got another sampling state in there as well, which turns my second order circuit into a fifth order circuit immediately. And then you say, well, you can't really build a switcher without putting a filter on the front. So it's got to be a filter on the input. So my fifth order switching converter is now, depending on how you look at the analysis, a sixth or a seventh order circuit. And then lots of people, of course, it gets noisy on the output, so a little post filter goes here, and now you've got, eighth, ninth order circuit. So 8 state variables if we don't include the sampling of current mode control. So we've got an 8th order system to deal with. If you want to get deeper into this and you start modeling magnetics, some of you will have seen our magnetics presentations in the past. You'll know that if we want to include the winding loss of the inductor, and maybe you could do the core loss of the inductor as well, we had a whole bunch more states to it. So adding AC winding resistance models, you've got 3 inductances in there, they can really affect the performance, the small signal performance. So it's quite common that the AC resistance of an inductor, filter inductors are rising quite rapidly in the region where we place second order filters. These are fairly high frequency filters here. And the whole damping depends upon the AC resistance model. And this converter now turns into 23 state variables. If you want to throw core loss on top of the mix, we're up to 46. So, how did this happen? Everything we analyze in university is like a second order system. Maybe you get advanced and you do a CPIC converter. You say, okay, well, I've got a 4th order system and I split that into 2 second order systems. But then you add a 3rd order feedback around it. So it's a 7th order system. Now we're up to 46 state variables in the system. And this is just a simple buck converter. If you add another 2 buck converters to do multi-phase on there, keep going, and then you add the power system in front and the power system afterwards, and the order of the system just grows out of control. So you can't do state space analysis on, 46th order system. You simply cannot optimize control around this. So, Vorpirian gave us the beauty of the switch model to reduce the central converter to just, a nice, easy, no state space averaging needed, circuit model, just like you were doing, transistor analysis. But he didn't talk too much about expanding the system until he got deep into his circuit analysis of where you looked at blocks interacting with each other. And of course, that's what Middlebrook was doing as well. So what was it that Bodhi did to us? He said, well, I don't care how many states you have in your system. And of course, he was dealing with high order systems as well. He's not dealing with the second order buck converter. They were dealing with all kinds of control systems for missiles and whatever they were doing in defense and Bell Labs at the time. And there was no analytical way to deal with such large order systems and control them until he came out with this Bodhi plot. And the Bodhi plot said, well, I don't care what's in there. I don't care what order the system is. Just draw a couple of lines on a piece of paper for me. I'll tell you whether it's stable or not. And, this is so profound to be able to do that without having to analyze anything that, there's really no substitute for it when you get to these large order systems. And that was the gift. So, this is just a buck converter that grows out of control, but then suddenly we've got this magical tool where you just go in the lab, you do a couple of plots on the screen, takes you a couple of minutes, and then you can make an assumption about the entire system, about its stability and its performance and how well it's going to work for you. So it's when you learn that and you know that, it's hard to understand why people are so reluctant to go there. And then, of course, it's back to the math again. Well, they don't want to deal with, the imaginary numbers and state variables and the size of the system. They just don't want to know. So they just want to kind of poke at the converter from outside and say, yep, good enough. Let's get it out the door. Right. But yeah, don't minimize what Bodhi did for us. It's an amazing thing. And yeah, this whole topic obviously is going to be about that. All right. Let's talk about frequency response. So two blocks against measuring frequency response. One is the math. You're not comfortable with the math, you're not comfortable with the imaginary numbers, or your manager isn't comfortable with the math or the imaginary numbers. And your manager says, well, we didn't use, that fancy equipment in my time, so we can still do it the old way and everything will be fine and I'm comfortable with that. And that's fine. So let's talk about frequency response analyzers now. And I think I'd probably have the unchallenged distinction of having tested more frequency response analyzers in the world than anybody else in the world. Most people get a frequency response analyzer, they use it for a while, maybe they use a couple of others, but we test everything that comes along. We're always looking what's going to help us next with teaching, with this, to get the price point where we can use it for lots of people. We need to know what's coming on the marketplace to change things. And my beginning of doing frequency response analysis was just a signal generator and a scope. So I had a signal generator. This was back in 1980. I had a vacuum tube power amplifier because that's what was laying around in the lab. And I was building an LLC circuit at the time. I didn't know that's what it was, but I've learned that since then. And I spent so much time in the lab just turning that dial on the frequency response on the signal generator and watching the output response, whoop, and down again, up and down again. I swept across that filter so many times. I spent months and months in the lab. And when you do that, it just sets it into your mind that, okay, this is a powerful tool. You can see the filter. You're not just looking at equations and manipulating them and finding cues. You can see it on the screen. You can feel the cue. You feel it jumping up and down. So everybody, can do that. Signal generating scope. If you don't have a signal generating scope, you might want to rethink your career and maybe go back into, I don't know, writing code or something. You can certainly afford that these days because scopes are cheap, signal generators are cheap now. You can get lots of scopes with signal generators in them, but don't minimize this effect of seeing the effects and controlling it with your hand. Sometimes having a software controlled signal generator isn't as nice as the old one with a dial on it. Kind of like driving a car. You can feel it. So that's where I started here. And if you click on the link here in your PDF files, it will take you to an article of how to measure magnetics the manual way. Okay, it's tedious, it's a little painful, but if you have no other way to do it, this is how you get your design done. And it'll teach you how to measure, open circuit of transformers, short circuit of transformers, to get the leakage inductance, and of course it's variable leakage with frequency. So there's much to be learned from doing that. So that was my college experience, was using the signal generator and scope. And then I went into industry and got exposed to all kinds of things. So when I went to Middlebrook's workshop in the early 80s, he used a narrowband voltmeter from HP. So this basically put out a signal and it had one measurement channel. So that one measurement channel would only measure that frequency with a very narrow bandwidth around it. So it's kind of like a transmitter receiver, but everything was analog. So you had a little analog meter that was giving you the reading of the voltage, and you just dialed it up with your hand and you tuned into that one frequency, that one measurement. And Middlebrook showed us how we could get gain and phase from a single measurement. So now we're trying to measure two signals in a loop. So we measure one signal for its amplitude, we measure the other signal for its amplitude, and of course I've got the relative gain of the two just by dividing the amplitude. How do you get the phase? You put the meter at the difference between the two. So now you're measuring 1, 2, 3, you're triangulating. And this is actually a very accurate way of measuring the phase between two signals. They can be very distorted, but it will pull out the fundamental, and it will measure the phase shift between them by using the cosine rule and the three measurements on the triangle. So that was the narrowband voltmeter. I'm not sure you'd even find one of these anymore. Sometimes I wish I kept these for a museum, because that was kind of fun. We got lots of loop gains out of it. At the same time, we had Dean Venable came into our company to show his Venable instrument, which automated this. So he was the first one to automate it. And that was $30,000 back in 1981. So that wasn't a low cost machine by any stretch of the imagination. And then the one that we ended up buying where I was called a Bafco 916XH. So again, I don't know, maybe you can find these on eBay, I don't know. And the beauty of the Bafco is 100% analog. You had analog dials on it, and they had logarithmic multipliers on them, and you dialed everything in and you tweak things up and down. And the thing that was really nice on the Bafco was it had a 10-volt source. So it was a fairly reasonable amount of power from the source as well. So they were the first ones to do that, which when you're driving a power circuit, as we're going to see, sometimes you need that powerful source. So we bought one of those instead of the Venable, because that was only 5K instead of 30K. And then I went to Virginia Tech, and we had the HP 4194 there. And we were so into doing control experiments there that they bought another one, and then they bought another one. So we had 3 HP 4194, 95s there, and they're still working in the lab today. I know they still run their labs with the old 4195. Fantastic machine, went up to 100 megahertz. Started at 10, which is a bit of a detriment these days, but they were tremendously expensive. So 1985, they were 55K a piece, and then you had all the accessories you put on them as well, which added a few more thousand. So you can still find them. If they work, great. If they don't work, it can be hard to repair. HP stopped servicing them for a while. I think they've started that again. But these can cost up to 7K just to repair the input channels, because nobody has the parts anymore for those. Next one down, which you can certainly find around, is the HP 3277. So it's kind of a little, little brother to these two. Not as powerful, but it certainly does the job. And all three of these machines, they really, they spelled the end of the HP era in this because they didn't have good software interfaces. You could write some HP Basic and download the results, but it was really bad and it wasn't structured around computer extraction of the results. So that led us to the AP era. So Alan Phillips of AP Instruments, he used to work at HP, and he could see this coming. He said, well, they're just not working on software. They're doing nice hardware, but it was time to move to the PC era was with us. So he came out with the AP 102A, the 102B, the AP 200, AP 300, AP 310. And we started working with him, back in the days of the AP 102, and then encouraged him, look, I really want this 10-volt source back. I want this power that the BAFCO used to have. So that showed up in the AP 300 and then in the AP 310. So this now has a 20-volt peak-to-peak source on it. And it's got a 2-ohm source impedance to go with that. So the power amplifier is built in all the way up to 30 megahertz. So that was AP, which is still the dominant industry in the market. It's the one that's full featured with the amplifier. It's got the best noise rejection. It's got input channels and not actually grounded. They're virtual grounds, so you don't have grounding issues. So it just gives a dynamic range that, when other analyzers can't quite cut through the noise, we always go to our reference AP 310, which will just, okay, here it is. And we'll show you some of those measurements a little later too.
Someone's telling us, John Pease is telling us that it's the HP 3577A.
Oh, sorry, 3577A, okay. Well, don't buy one anyway, John. It's it's just, if you can find these old machines, you might think you're getting a bargain, but the amount of pain and time it will cost you, the 4194, 4195, or 3277. Sure, if you want to do some RF work, great. Do that. They're very cool machines.
Yes, 3.
But yes, 3. All right, John, great. You have 3 times as much pain then. And then one of the things we had on the 4195 and the 3277, we can see you have to change signal size as you sweep a loop. And they made it somewhat easy by a little up-down button. So you're watching the loop gain chunking along and you'd hit the down button to reduce by 60 dB and down and down and down. And if you didn't catch it in time, you got a distorted curve and you have to start over again. You couldn't save the size of the cursor that's sweeping there. So Alan Phillips, he worked for HP and then he created AP Instruments, and being an American engineer, he said, well, I can do this just like HP can. And he started his own company and took a second mortgage on his house and ran up his credit cards and released a product that was a fraction of the price of the HP and started selling that. And it was about 10 years later that HP decided to exit the business because they couldn't compete. They just couldn't re-engineer the 4195, and the market of, the RF market, the analog market had shrunk, that it wasn't worth being in there anymore. So we recently come out with we also offer for our teaching, we developed the Ridley Box. Originally just for teaching, but people like it so much, we're selling quite a few of these. And this has the unique characteristic that we pay you to take the analyzer. Okay, it's not just free. We actually give you $500 to take it because the scope is $2,500 if you try to buy it. The isolator is $600, the computer is $1,000, the design software is $2,400. So the analyzer turns out to be a $500 rebate there. So, think about that. And, are there more? Yeah, of course, we've tested everything. So these are the also RANs to us, the Newton's Fourth, the Core Technology, Digilant, Agilent, ARC, Omicron, Cleverscope, Tektronix, Roden Schwartz. They don't do too bad job, Tektronix and Roden Schwartz, on their measurements, but they don't have any setup for you. The hard part is that lots of times we go into a company and we'll go in there and we'll even see the APs. Say, hey, you've got an AP, you're not measuring loops. It's like, well, or they got a Venable sitting on the shelf. It's like, well, nobody remembers how to use it anymore. And that's where we come in. We've written our software to interface with that you connect the AP or you connect to the Ridley box and you click a button, the setup is done. So your measurement has the highest chance of success. If you just open up an analyzer and run with it, you know, it's like, well, what do I do with this? And there's so many settings. I don't know if you remember, I'm sure you remember, John, the 3577, the 4194 and 95. There's so many buttons, hundreds of them all over the machine, and you got to push them all at the right time to get a good curve. Same thing with the modern ones too, and you need help in setup, and that's what we work really hard on doing. Okay, so it's a great time to do frequency response. You know, in the just before AP came out, and even after AP came out, there really were only a handful. And it was kind of a dying thing to happen. But now the scope companies have discovered they can kind of do it too. So you've just got your choice now. There's no excuse saying I can't find one or I can't afford one. You can certainly afford one. Okay. So that's good. It's a great time to be in frequency response analysis. It's really encouraging to see this because with the computer generation, they were trying to say, okay, that Bodhi plot stuff just isn't relevant anymore. And they were just missing out on the best tool for solving complex control problems. People asking questions. Yeah, we'll have a recording, of course. We always do. Input filter damping, Clyde. Yep, I see your question on that input filter damping. That's a horrible input filter. And one of the presentations we were going to do at APEC last year was how to damp this filter without adding damping. And we succeeded in doing it, and we prepared the presentation, and it's been sitting in my box for a year now, and I've never presented that work. But we just add 2 or 3 components, and we damped this input filter, which everybody says can't be damped. So that's cool work. It'll be coming. We've just been so busy with everything else here and with our workshops that we haven't gotten to that. All right. I don't want to show the answered questions, do I, John? Okay. You check them as answered, yeah, okay. All right, going way back when to the beginning of switching power supplies, there were always 4 essential measurements that got made. And if you were in aerospace or you were building things for the space station or NASA, you had to make these measurements. This was just, if you wanted to interface with the world, they said, okay, where's this? I need to see that before I'm going to buy that block from you. So this was just standard back in the day. And some of it's fallen by the wayside. Some people have tried to emphasize this measurement versus that measurement, but nothing has changed on this in all this time. And the first one, of course, is the loop. Okay, now the loop we're going to find out is the most crucial measurement to make. And in some ways, it's the most difficult because the power supply manufacturers like to hide it from us, and the app notes like to hide it from us. But it's the most revealing measurement that you have for the health of your power converter. Your entire system, the health is reflected in the loop measurements. So we're certainly going to make some of those today. The next one is the output impedance. Okay, you're going to measure the output impedance of the converter. That will tell you how good a voltage source that you've built for your system. So if you're going to interface this power supply to something downstream, you know, maybe you're a class D amplifier and you've got to look at the impedance of your speaker and you look at the impedance of the class D amplifier, you'd better be low impedance relative to that speaker, otherwise you're going to hear some strange things going on. But low output impedance is a design objective of this power supply. How do we get there? By putting a good loop on it. Okay, so this is the design tool. This can be the objective. So that's the output impedance. Next one is, I don't know how to draw an arrow here that represents this. Maybe a double-headed arrow would have been better, but I'm always a bit late doing the presentations here and getting everything working. Audio susceptibility is the input noise to output noise. Okay, and it was called audio susceptibility because early switches were just about 20 kilohertz or so. And any noise you injected into the line, you could hear it, right? So you were injecting audio frequencies. You go up to the switching frequency. Beyond that, it's not about control loops anymore. It's about layout and capacitance and, you know, little sneak through paths of EMI that communicate the noise from input to output. So this is audio susceptibility on the input or power supply rejection ratio measurements. And that's had an interesting history. As I said, in the beginning, everybody did it all the time. And then, as I hope we get to this measurement, when people went to current mode control, it became so low you couldn't measure it anymore. I mean, it's just below the noise threshold of any analyzer that you have, so you can't see it. So people built current mode for 10 years and 20 years, and they didn't question why they should do current mode. They just knew that, and everybody kind of stopped measuring the audio susceptibility anymore. And then the last 5 years or so, people started measuring it again. Why? Because they stopped doing current mode, or they've done LLC converters where they're just worrying about efficiency and they've forgotten about the importance of the loop, and they can see noise on the output again. Sometimes it's terrible noise on the output. So now people have started speccing and measuring line to output or power supply rejection ratio. So that's important. Last one is the input impedance measurement, where you perturb the input and you measure what the impedance is. So this was really important when they were building the space station. So they were building these big blocks of power. They would shoot them up into space and they say, well, we want to add this source, or we want to add that source, we want to add that load to it. How's it going to react? And if the input impedance was high enough and the output impedance was low enough, they could say, well, it's not going to react. This is Middlebrook's, you know, input filter problem or extra element theorem, whatever you want to call it. If you make it a low output impedance, high input impedance, that block is kind of impervious to whatever you might load it with or provide it with. So that was the whole reason to measure this and this. Noise reason is obvious. And then the loop, of course, is what is controlling things like input impedance and output impedance. Input impedance is of particular interest because in every converter that you build, assuming it's got some efficiency, will have a negative input impedance. And you all know this, when you're sitting on the bench, you dial up your input power supply, and then when it hits regulation, the current starts to drop. So that's a negative resistor, and that negative resistor likes to talk to anything ahead of it and excite it and make oscillations. And that's kind of how the whole field of analyzing power electronics got started at Caltech. They built a power supply, they put it in a submarine, oscillated like crazy, and that was the input filter interaction with the negative impedance of the power converter. So that's important. While this is important, it's probably the most misinterpreted and the most badly used. So when people strive for low input impedance or high input impedance, very often they're defeating the point of the power system. And Middlebrook's talk about the interaction on input impedance is a very specific case that doesn't include the input filter, and you never measure that. So that's why that measurement is like, yeah, you can measure it if you like. I suggest you actually predict it and then put the demarcations on the power system where they belong. But you know, that would be the topic of a more advanced separate webinar. Maybe we'll do that when we stabilize that filter for whoever asked that question. So let's start with loop. So Middlebrook insisted always measure the loop. It's an integral part of his course. And you have a switching power supply here and a PWM controller here and a loop around it. And the technique is to take the signal source, this can be a signal generator or the source from an analyzer, and you isolate it with respect to ground, and you impress it differentially across a resistor here. Now, Middlebrook didn't even use a resistor. He just put a little loop of wire in his circuit, and he put a current probe around it. So he'd clip a current probe onto the loop, and then he'd inject into the circuit, And that worked. That gave you, you know, some maybe tens of millivolts of signal to measure. Isn't really enough for a high performance system, but that was another way of injecting here. But the idea is you inject a signal differentially across the resistor, and then you measure the output of the loop divided by the input of the loop, okay? And we're going to do a little simulation in a minute to show you how this works, because it's kind of a curious thing. And I don't know if he invented this technique or he got it from somebody else. Probably somebody will have a reference of where that came from. But the important thing is you're measuring the open loop of the converter while the loop is closed. So this 20 ohm resistor makes the converter regulate, but I can measure the open loop. Because of that particular injected frequency, there's a difference between input and output of the loop. Therefore, I can measure those two signals and see my open loop gain. All right, so we're measuring open loop gain with the loop closed. Now, why is this so important? Well, it's important, one, when you're in the design phase, you're going to optimize the design. You're going to get as much gain as you can where you need it. You're going to get the crossover that you need. You're going to get the phase margin that you need. You're really going to work on massaging that loop and the compensation to give you the best performance out of the loop. So if you skip that step, you know, you just don't have an optimized design. You know, you're not getting the best performance out of your system. The next thing that most people overlook this is that measuring the loop is a really revealing verification of your manufacturing build. So there's so many components that are involved in making that loop what it is, and it's so sensitive with gain and phase that if there's something wrong in your build, certainly if any of the compensation components are wrong, but you know, the upper cap, the upper inductor, a loose connection somewhere, you're going to see it in the loop gain. So there's a lot of companies that do 100% loop test in their production supplies. It just goes down the line, measure the loop, yep, it's within a certain band, great, it's good. And that is so revealing. So, you know, when we run our workshops, you know, the most common mistake in the PWM controller is they plug in the wrong values. It's not 3.3 nanofarads, it's 3.3 microfarads, or, you know, it's off by an order of magnitude, okay? Maybe it looks okay. Maybe it's got such low loop gain that nothing looks unstable. The step load might look all right, but you measure the loop, it's like, oh yeah, we missed by, you know, 40 dB on that. Let's find the component. So this is really important for verification of the build. And then of course, maximizing performance is, you know, crucial.
We've got three questions, right?
Okay, stop.
Roughly the same subject. One is about the injection point for multi-loop design. One's I said Middlebrook invented, I think, but what about when you can't break the loop like the regulator has in stereo feedback?
Yeah, there's, you know, let's if you can break the loop and measure it and work hard to get that done. Are there systems that you can do that? Yes, and we're going to cover that, you know, in a little bit. But if you can, this is such a revealing test. Nothing reveals the operation of the converter like the loop gain. So, you know, what was the other one, John?
Yeah, they're all saying, oh, if you can't break the loop again, and then multi-loop design.
Yeah, multi-loop design. There's, you know, if you look at our current mode systems, there's 2 loops in there that you have to measure, but measure something. Measure something. I mean, my early days when we first got our BAFCO at work, we had all these power supplies coming in the door. I just measured everything I could find. It's like, wow, look at that. That's a good, curious loop there. And what they did another feedback loop from the output, and they got a negative output impedance as well as a negative input impedance. That was cool. Every loop you look at will tell you a story, okay? And you'll find the right one to measure. But again, are there times when we can't? No, but that's maybe the 10% cases. Maybe that's growing these days, as we're gonna talk about in a little bit. But if you've built the loop, if you've done a controller, please go and measure it. Okay, it doesn't make a lot of sense not to do that these days. Okay, I think that covers most of that, right, John?
Yeah, yeah. It's like, you know, regulators with internal feedback. And if you
Right.
can't
Yeah,
Yeah.
yeah. There's some systems you just can't measure them. And some systems you have to not use them because you can't measure them because you can't get the performance out of them. But we'll show you some of those in a little bit. When you're doing this, by the way, you need this isolator. Oh, did Venable invent the method? No, I'm pretty sure Venable didn't invent that method. If Middlebrook had it in his course that far back, you know, people were measuring loops before then. So could he have invented it? Maybe he did. I don't know. I've never found the source for who came up with that. But I would probably attribute it to Middlebrook because they were the ones that were running into these issues the earliest. So when you do this, you do need an isolator. So, you know, when we first saw the Venable on the market, you had to buy 5 different isolators. So one went from 10 hertz to a kilohertz, and you had a kilohertz to 10 kilohertz, and 10 kilohertz to 100 kilohertz, and so on. We put it all in one. You know, get 0.1 hertz to 30 megahertz. That's 8 decades. It's a pretty remarkable device here. If you feel like winding your own, be my guest. Okay, you won't get this range, but you might cover the range that you need. But remember, you know, count your time. You know, we put a lot of work into designing this thing and building these things. So, you know, you might as well just buy one, quite honestly. Even though as engineers, of course, we all like to wind our own, and you can do that. But you've got to have the isolator to float the signal across here. Step load testing. I'm surprised nobody's said this. Maybe that's because you're on a frequency response webinar and therefore you're open to it. But you will run into people in the business that, nope, don't need that. I'm going to do step load testing. And we've always optimized our loops that way, and we always will optimize our loops this way because I don't like these imaginary numbers. And step load is fine. If you do a step load and it's nicely damped, it's like, okay, that's fine. Your system is probably got a good phase margin, but you can't see, what if I cranked up the loop and made the step load better? You can't see that coming. When you look at the loop, you see that, you say, hey, I'm only crossing over at 1 kilohertz. That could be 10 kilohertz. Step load's not going to tell you that. So there's no design information there. There's only information about what is right now, not what could be. So this is an article you can go read in our design center, 3 different step loads. Okay, and they're all oscillatory. So it's like, oh, okay, something's wrong in there. Every single one of these systems has a different solution. And the problem with the step load is like, well, I have no idea what I'm supposed to do to fix this. Should I move the gain down, which is the answer to one of them? Should I move the gain up, which is the answer to a different one? Or should I do something else in the compensator, which is the answer to the third one? Okay, but when you look at the loop, it's like, oh yeah, look, that's not right over there. That 0 is missing. You know, this is wrong. You just can't see it in the step load. Do we do the step load? Of course we do the step load because that's what the customer's going to do. It's part of our experiments, but it's very hard to capture it sometimes because it's so tiny, and you just don't get the wealth of information that comes in from a loop. Okay. So, any more questions, John, or we're good?
Yeah, there's one that said, how can you close the loop and claim it's an open loop measurement? So I'm just answering that right now about closing the loop, the crossover frequency, and observing above that crossover.
No, it's actually not that. It's here you're injecting a signal across the resistor, right? So you're forcing a voltage across that resistor. And at that one frequency, the loop is effectively open because there's forced to be a difference between these two. So this is how you get an open loop measurement while the loop is closed, because the signal itself opens the loop and every other frequency is closed. Okay, so this can be a high bandwidth system here, but I'm breaking the loop with the signal. Okay, very clever technique. Again, I'd love to know who created that. I see Bob White, I think, is on the list of people here. Maybe you know, but maybe Bodhi himself did this. I don't know, because every high gain system, you can't open the loop. You've got to keep it closed, and then you've got to measure the open loop. So the need has been there for a long time. There's a lot of clever people that went before me and went before Venable and probably Middlebrook as well, all the way back when they had to measure these things. So try that one. All right, let's see. Let's do a little bit on how this injection technique works here. So you can sweep a real circuit, which we're going to do, but you can also sweep LT spice. So this is a fairly new ability for this to work well. So right here, what you see on the screen is LT-Spice. And we've got a little converter here, and then we're injecting a signal with an analyzer. So we built a model here that does all the hard work for you. You know, you can get these sub-circuits from us if you like. So you've got your own little analyzer. So you can connect it to any circuit and you can run a sweep. And we can look at the signals here. So let's run that circuit. And what we're going to do first is probe our injected signal. Oops, bouncy model. I'm going to measure the injection. Didn't get it. Didn't get it again. Sorry, be there in a second. There you go. So this is the injected signal that's going into this circuit. So we're measuring a 2-switch forward converter here, and it's measuring the injected signal across the resistor. So right now we're just doing a fixed injection. It's a 1/2 volt injection into the circuit. Okay, and you can see it sweeping. It started at 300 hertz, a little bit higher, and then it's sweeping a 100 kilohertz circuit. Okay. Now, some of you will be saying, well, yeah, you should be using Simplest or PSIM or something, but don't always be in such a hurry, okay? Yeah, we could do this in PSIM or Simplest in a few seconds, and then the results drops out, and it will be terrible. Sometimes it's good to just slow yourself down and watch it happen, because there's a lot to be learned here. So we can see the injected signal, it's constant. This is what's breaking the loop. All right, now let's look at the other signals. Let's just look at channel B, which is the output of the loop. Okay, so here's the output of the loop now. I'll get rid of the injected signal first. You get the point that it's not changing. And we'll delete. So here's my output signal, and its amplitude is just about equal to the injected signal, okay, because we've got a high gain loop. So this injected signal of 0.6 volts has to distribute itself according to the loop gain between input of the loop and output of the loop. And right now, because the gain is high at these frequencies, it's all showing up at the output of the loop. Okay, so now let's look at the input right here. Okay, and now you can see there's only a little bit of disturbance on the input to the loop. Okay, so again, these are the same signal point tied by a 20 ohm resistance. The difference between this signal and that signal is the injected signal, right? Get rid of B. And now we see the perturbation on the input of the loop this is 12.55, this is 12.6. So we're talking about 50, 60 millivolts on this signal versus 600 millivolts on that signal. So at this point, we got about 20 dB of gain in the system. And you can see the signal here is growing, okay, because the loop gain is going up. So this signal gets smaller, the other one staying constant, and then it gets a point here where it actually goes down a little bit, because that's where we're approaching just before the resonance of the system, okay? So this, you know, looking at these waveforms, studying this, you know, slowly, watching them build, is where you learn how this process is working, okay? And we'll keep on going here. And then, still sweeping. Then we're going to look at one more point, by the way, is the control voltage that comes out of the error amplifier. And let's delete BA. Okay, there's the control voltage coming out of the error amplifier. Okay. So as we're sweeping along, you know, that's changing its signal size. And we're going to hit a point where it starts growing in a little while. Okay, let's leave that running. Okay, Spice likes to take its sweet time. Okay, but again, instructor, now you can see that signal size there started to grow. It went through a little bump, then it came down here, and now it's started to approach the crossover signal. So the two signals are going to shift. The A signal is going to get bigger, then it gets multiplied by the compensator, and we can see that there's more and more modulation appearing on the output of the compensator here. Oh, there it is, taking a big jump there. And then just a couple more. I had to rescale there because it's getting bigger. Okay, 0.8 volts on there. Have more questions there? Where can I get the sub-circuit of the analyzer? We can send it to you. Send us an email, and we'll post these somewhere as well. Is this? Right, you can't use. You can use the transient response again to tell you, are you absolutely stable? Do you have better than, let's say, 45 degrees? Absolutely, but if you don't have it, you can't see what to do to change it. There's just no information there. So now we see the problem in this loop. We see we're getting more and more modulation on the output of the error amplifier, and we're going to hit a point, you know, where this signal gets too big. Okay, we're injecting the same size signal, of course, across the resistor here. This one is shrinking, channel B is growing, and then channel C is growing even more because that's getting amplified by the feedback amplifier. Okay, growing and growing. Where would the 20 ohm resistor go for constant current regulation? You have to see schematics, always on these questions. Where do I inject? It gets very detailed. You know, you have to send us your schematic. We look at your schematic. Okay, you need to inject here. Okay, of course, we got finite bandwidth for looking at everybody's schematics, but everybody's got a unique situation. Sometimes 3, 4 loops in the system, and it's not clear where to look, and you just got to do some engineering thought on what you should do next. So now we see how this error amplifier is growing on each sweep. Okay, 2.4, and we're going to see something interesting happen in a minute. Quite a big change on each sweep here. And this is obviously not, I see what happened there. It went all the way down to 0 volts. So my error amplifier now is railing out at the bottom end. Okay, so I'm overdriving the system. And you can see that now it's overdriving on the top, and it's clamping to the peak voltage of the error amplifier. Okay, so if I tried to plot this loop gain with that constant 0.6 volts, I would get terrible results as it approaches the crossover here, because I'm just saturating the amplifiers and everything's nonlinear at this point. So you can't use these results. We'll leave that running. We'll come back to that if it makes sense. All right, hope that taught you something there. Can you get that LT Spice file? Sure, we'll send you that LT Spice file. Maybe we'll make it available, or I don't know how we're going to do that, but let you know. But we'll send you an email if we get that going. All right, anybody out there who works for the semiconductor companies or people that write app notes, please pay attention to this slide, because while we all recognize that loops are important, there are many machines for measuring loops. Everybody wants to do it now. When people are making app notes or designing their power supplies, they're making it harder and harder and harder to cut into the loop, which is why they say, well, don't do that, measure the impedance instead. It's like, okay, just put the injection resistor in your design, please. Give us a couple of test bins if you can, but you don't have to do that. Even if this is a design for in-house, on your schematic, your main schematic, you've got the divider resistor in your compensator. Above that, you want the 20 ohm. Just put it on the circuit, okay? Because you might need it one day. If something's failing in the field, it's got a weird load with it, and you want to measure the loop. If you can't get to this trace, you know, it's a real pain. We spend so much time cutting into circuits trying to fix it. So here's an example of an LT board, 402 resistors. So we had to tack onto this thing, put a resistor across it, put a couple of test leads on there, okay? They made it as hard as they possibly could to get in there and do this, which is crazy because it's an app note board. You'd like to fiddle around with things and crank up the loop if you can. You know, you got different loads coming along. You got to be able to tweak the loops and make it easy. If it's your own design, the reason I say to put this resistor in, because if you put the resistor in, it forces the layout engineer to bring the traces to the surface, to put that surface mount part on. Otherwise, they might bury the feedback on an inner layer back to the control components, and you can't get at it. So then you've got a tombstone components, and it gets even more difficult. So do that in your own designs. Please, if you're doing app notes, do this. Here's the latest board from EPC. I don't even know what size these parts are there, but I'm just not going to go there. Okay, I can't. It's a 16th bridge motherboard. I'd love to know what the loop is, but I can't look at it. If you're going to add your own load capacitance, you've got to be able to measure and look at what happened with the load that you're going to use, and then measure that loop. But you know, it's getting buried. So on the one hand, in the industry, we got this awareness, yeah, we better always measure this loop. On the other hand, it's like, okay, we're going to make it more and more difficult for you to measure the loop. So they just don't go hand in hand with each other. All right, enough. I think everybody got the point on that. If you have any app note people, just give us a.
Why 20 ohms? What 50 or
why 20 ohms? 20 ohms is, well, most analyzers have an output impedance of 50 ohms. So if you put a 50 ohm resistor in there, you'd get the maximum signal from it. However, if you put 50 ohms in there, you're going to disturb the set point a little bit. So 20 ohms, 10 ohms, it's not really that crucial, quite honestly, what the value is, but 20 ohms is just kind of a sweet spot in there. 100 ohms is definitely too much. You're definitely moving the set point of the controller when you're putting 100 ohms in there. So again, nothing magic. Middlebrook, of course, didn't use a resistor at all. He just had a loop of wire and made it part of a transformer. Okay, and then the only problem with that is the signal size is not gonna work very well. That take everything.
Yeah, what's a good rule of thumb when hooking up to grounds?
Right, pay attention to grounds. It's like I say, it's experience. If you're measuring 60, 70 dB loop gains, you know, you've got to have things grounded properly. And that doesn't mean necessarily everything grounded. Okay, you've just got to, you know, judiciously ground things to get the results that you need from the system. But it's practice. Okay, there's no rule that tells everybody ground this, don't ground that, ground this. Every system is different. Okay, but if you don't measure, you're never going to learn. Okay, setup. Let's do this. Okay, so here we have, if you look on your camera, you should see our test setup here. I was going to have this set up in advance, but that's kind of boring. So what we do first is take a cable and we connect our source to our isolator. Okay, so one thing we've done with the Ridley Box is we got this great big injection isolator inside that box there. Okay, and you see it doesn't actually fit, but we're magic at doing these things, so we made it fit. Okay, so that's in there because, quite honestly, I get tired of seeing these cables strapped all over the bench. You got this box and that box and that one. So we had a little space inside the box there. So we put it, as you can see, inside here. That's the input to the isolator and the output from the isolator. That's step one. Step two, inject it into the loop. So here's my little loop injector right here. Little clip lead. Of course, you could use a BNC cable to go a little further if you wanted to. But you just clip, input, output, right there. So now we're injecting into the loop with those two wires. Step three, channel A. That's this one here. Channel A. I've got my choice of grounds here, but I'm going to ground everything as near as possible to the output. So channel A is the input to the loop. So I'm connecting this probe to channel A right there. Okay.
Microphone is hiding channel A.
Is it? Okay, sorry about that. Okay, so channel A on the box, and then channel D on the box. Could we use channel B? Yes, we could. We get better results with channel D. Lots of reasons for that, but we'll go into that right now. Channel D, right there. Okay, you're done. That's it. That's all you need to do to measure a loop. How hard was that? So, as long as you got the resistor and the test points on the board. The hardest part put in the resistor into the board, put in the test points into the board. Okay. Those of you who call us for consulting work, oops, what's going on here? There we go. Consulting work and you want a loop gain, you know, your bill will be lower if you have an injection resistor on the board, and we'll probably blow up less of your boards too. So think about putting that in there. All right, there we go. Let's give it a go. Escape. And we're going into our little program here. Let's go right into the analyzer. Okay, so here is our analyzer. And we've got it turned on. And then the first thing you do is you click on loop gain.
Use this Ridley Box setup for measuring loop gains.
Okay, so just to help you again, remember I told you a lot of these analyzers, people have them, they're sitting on the shelf, nobody knows how to use them. We give you a reminder. Here's a little picture, how to measure the input channel, output channel, the source, and so on. And we set the size of the source here. Okay, so it's starting out at 2 volts, and then it drops, and then it ends up at, let's see what the source is. It ends up at 0.1 volts in this case. So we've got a 20-to-1 difference between the initial injection and the final injection. Okay, and then you've got the different frequencies at which those values kick in. So we can move these around. If we just click those to the right, you can see the source moving there. Okay, that's easy to do. And you have the option of doing a fixed source as well. If you want to see the distortions with a fixed source, you can do that, but let's not do that now. And then we turn on our power supply. Hopefully all the lights come on, they do. And then we click sweep.
Sweep initiated.
Okay, and then we can see our sweep coming in here. Got 60 dB of gain down there. Many of you will have noticed, by the way, our analyzer talks to you, and it becomes kind of addicting, actually. I get a little disconcerted if I don't hear the analyzer working anymore. So that was a nice touch our programmer put in for us to have it speak. So here we're sweeping from 10 Hertz, 20, 30. Now the gotcha on loops, always, always, always start at 10 Hertz. I don't care if you're switching at a megahertz or 10 megahertz. I want to see the loop start at 10 Hertz. Why? Because the most important piece of noise coming in is at 50, 60 Hertz or 100, 120 Hertz. So you have to sweep that region. Make sure there's good loop thing in there, good impedance we'll look at later, noise rejection at that point, but you always start at 10 Hertz. And that's why every analyzer you find, the old HPs, they started at 10 Hertz. Okay, that's the magic number where you go from AC to DC coupling, and it's also less than the line frequency. Same thing on a scope. What good is a scope if AC coupling won't measure 60 Hertz? Okay, it's not going to help you very much. So always 10 Hertz is where you start these things up. And the old HPs, of course, you know, that's as low as they went. If you're doing power factor correction measurement, then that start frequency has to be about 0.1 Hertz, which is why we designed our transformer down there. Because you want to see all the gain, you want to make sure the compensator is doing its thing. I don't know if the noise is coming over the, you can hear your circuit. Can you hear that, guys? You hear that tone stepping? Sometimes when people are in our course and they hear that tone for the first time, they quickly shut off the power supply because they think it's going to blow up. Okay? But you should hear it. You should hear it sweep. Okay. And then we're getting there. We're sweeping at a fairly low bandwidth right now. I think it's 10 Hertz. We can go down to 1 Hertz, or we can do 100 Hertz if you want to go faster. Advantage of the AP, of course, it will sweep faster, but you know, this again falls into the category for me is don't be in such a hurry. Look at this as you go along and try to figure out what's going on here, rather than just rushing to collect the data and then move on to the next part. This is an important part of your design process. Okay, let's look into Ridley Works. And let's look at our predictions.
You are using voltage mode control.
So here's our predicted loop. And here is our measured loop. Okay. So really good agreement. Whoops. I heard a very loud noise there. That's when it mixes with the switching frequency. It gets extra loud, and then it's done. Okay, so really good job down here. Really good job down up there. We start to lose the phase at higher frequencies.
Complete.
Okay,
Good phase margin more than 50 degrees.
Okay, so our little box even gives you the blessing of what the phase margin is and tells you it's good or bad and gives you a little pat on the back so you can feel good about that. Maybe if it's less than 30 degrees, it should be call Ridley Engineering for help. I don't know. What do we notice in deviations here? This is perfect. The gain there is perfect. The gain there is perfect. The phase around the resonance is, well, you know, that's 10, 15 degrees off there. Same there, which means the Q of the resonance is bad. Okay. And then, let's say the op amp is probably giving up here. The gain bandwidth of the op amp is very often not what they say it is. And that's why we keep these sweeps going beyond the crossover. You got to see, well, what's happening here? This is dropping off, right? Do you worry about these differences? Well, you can try redesigning this and making the final capacitor of the compensation a little smaller to pull the phase up. Or you can say, well, I'm crossing over here at almost 10 kilohertz and the phase there is just about perfect. But now you're in the dilemma, okay, do you work harder on modeling? You can't work any harder on measurements. It is what it is. And, we can't account for that, Q difference. And, we can certainly work on the op amp model a little bit, but it is what it is. If you've measured the loop and you've gotten to this point and you've gotten this 64 degrees, you're ahead of, 70% of the industry that never makes the measurement. And we're looking for here is the crossover to be good, about 1/10 of the switching. We want the gain at the resonance to be nice and high so that we can't see the resonance. We want the gain at the line frequencies to be as high as we can. So we want to keep just pushing this gain up as hard as we can. Okay, so the whole loop matters. And then once it's crossed over, you will run into systems, especially those of you with multiple loops, where the gain can start approaching 0 dB again. So you're looking for gain margin in here as well. How far is this there before it starts going unstable? Now the phase, again, it goes unstable in the measurement. About that point, you never try to cross over there anyway, but the predicted phase never goes unstable. So you kind of get a false sense of security from the prediction, and if you don't measure, you don't realize, well, it's not really going to behave that way. Okay. Somebody asked about me twisting the wires going to the output. Quite honestly, that's just for neatness. We're injecting fairly low frequencies here, and then we're shorting the injection wire with a 20 ohm. So if we were to pick up RF, the 20 ohm resistor would take care of that. But yeah, I just try to be neat with cables. You don't create loops and mess. And one of the things we have to teach people in our lab is, when you have these cables on your bench, most people have a lot of junk on their bench too. And the power supply moves forward and then the cables drop down into their lap. Not a good idea. Okay, we try to push the cables back onto the bench, because if you stand up and you grab a cable and it's a high voltage power supply and it lands in your lap, it's fun for people to watch, I suppose, but not to do. Okay, so there you go. So we've got a measured loop.
Does it have the load on?
Pretty loop. Yeah, you absolutely have to have the load on when making these measurements, because without a load, the converter isn't running in its region of operation. So I think maybe in my pictures I didn't show it. Yeah, obviously, yeah, you've got to connect the input bias here and you've got to connect the load resistor here. I'm just trying to show the cables. So it's like a 1, 2, 3, 4 step process, and you have a loop gain. Okay, so don't be afraid of this. Okay, this is easy. And then you start learning, okay, what's too much signal? What's not enough signal? What's the bandwidth supposed to be? How should I make all this work? So get in the lab and do it. These days, if you're a university student, you know, please find a way to measure loops when you go into industry. Because when you go into industry, they're not going to ask you, okay, please analyze this fifth order system for me and do pole placement. They're going to put you in front of the bench and say, okay, measure the loop for me. Okay, so don't be caught cold on that. Practice this as much as you can in the, you know, during your university careers. When you have time, you can do the signal injection, the scope method, but this is such an important lab tool that you're going to use at work, that you don't want to show up and say, well, I don't have that tool. I only know the theory, because we never measured it. Any professors out there, okay, please find a way to have your students start making measurements. So much more important than, you know, another analysis. Just a little comment on that, by the way. Let's see.
So does the loop analysis make sense of frequencies above half?
Does the loop analysis make sense at frequencies above half the switching frequency? No, it doesn't. It's wrong. Sorry, let me find my loop picture again. But, you know, it's not the only place where it's wrong. So the Q wasn't right compared to analysis. At half the switching, well, there's the switching frequency right there. And here we've got a half switching frequency where it actually looks pretty good. But is there any point? No, there's absolutely no point. And in fact, if you go back to the basic model that Middlebrook did and Vorpirian did, everybody did, there's all kinds of switch models, there's state space averaging. Every single one of them is fundamentally flawed and wrong. And it misses on this critical part of the Q. I mean, this is kind of a big miss. You'd think, wouldn't you, people would have nailed this by now? How can we be 40 years on from state space averaging, 35 years on from the PWM switch model, and we can't hit the Q? And Vorpirian has actually even come into our program here, and he's given us his latest calculations of Q. We've added proximity loss modeling, and we still always miss the Q. And we miss the Q for a very good reason. It's that every model out there assumes the output of the error amplifier is DC. Right, Joe? I mean, how crazy is this? The output of the error amplifier is done from duty cycle to output, and assumes there's no ripple in the output of the error amp. And of course there's ripple in the output of the error amp. There's lots of it. Okay, you'll see 20, 30, 40, 50 millivolts in there. That's got a little bit of current information in it too. You see the ripple on the converter, that's the ESR times the current, and then you amplify that and you phase shift it, and it's a significant little chunk of feedback of current there. So this is my latest theory
You are using voltage
of why the Q always misses, because there's always a little bit of current feedback coming from the ripple. Has anybody tackled that? No, because the analysis would be just ridiculous. But you have to accept that when you're done, okay, measurement wins. You can't change that. Measurement is going to be different. The measurement is going to win. And you can do a PhD dissertation if you like, trying to match this Q, but nobody cares, because there's the Q in the forward path, the Q in the return path. It cancels out. And the world isn't going to, you're not going to change anything about this industry by getting that Q better. Okay. The models here, as you start lifting up the loop gain, there's so much ripple comes through that the phase deteriorates when the model says it won't. So you push 20, 30 kilohertz, it's like, well, what happened to my phase margin? It said I should have more, but it doesn't. So yeah, the modeling is just not that accurate. So it's this accurate. So here's what I'm talking about. Okay, my loop is now a verification that this gain, the measured gain, tells me, yeah, you built it like it was supposed to be built. You know, you had these compensation components, right? There's no way you didn't put these values in. Otherwise, you wouldn't have hit this asymptote here, and the phase at that point. But we don't know about the Q. Okay, so, you know, different things you're using the loop for. Those of you who have reverted back to voltage mode control and are worried about this Q and how sharp the phase drops, it's like, well, stop doing that is probably the best advice I could give. Try to find a way to feedback some current and not worry about the Q so much. Let's go back now. Any other questions, John?
I'm getting through them here.
Okay. Can you display multiple Bodhi plots? Yes, you can. And you can do this with the AP300 now as well. For example, save dataset 1, voltage mode, save. Boom. Let's make it current mode. This is not something you can do as easily as us at home, but we just take it out control board, which is voltage mode. We put in our current mode controller. Plug it in the right socket. Turn him on. Everything's working, and let's sweep it again.
Sweep initiated.
Now we're measuring a current mode system. You see what happens down here? We got so much gain. We're having a little more trouble getting a clean signal there, so let's stop that for a minute.
Sweep cancelled.
Let's crank up the 2 volts to 4 volts. Give us more signal to measure. Okay. Let's sweep again.
Sweep initiated.
So that should clean it up a little bit. You see the gain cleaning up, the phase is cleaning up here, but now you're getting to the resolution of, you know, the AP can do this. It'll go 90, 100 dB, no problem. The other analyzers, which are not our AP, they don't have quite as much resolution. But hey, you know, look, I got lots of gain here. Do you really care if it's 80 or 90? Not so much. So now we've gone current mode, and we're comparing a current mode loop with a voltage mode loop. While that's sweeping itself, let's go do that in the prediction too. We'll change it to current mode. Okay. So that's all good.
You are using current mode control.
Okay, so there's our current mode prediction. I'm sorry? 4 volts peak to peak, yes. 4 volts peak to peak. The AP analyzer, for those of you that have them, have it in RMS. So 7 volts RMS is 20 volts peak to peak. Okay. Okay, somebody's asked the question, what do I think of the argument put forward? The Bodhi plot doesn't show you stability in non-minimum phase systems. I think it's, I think somebody's reaching to write a paper or sell a product, quite honestly. Every converter is a non-minimum phase system. It's got right half plane zeros in the current loop flyback system. It just works, and everybody's used it. I mean, if everything were a simple first order buck converter type thing with no minimum phase, then you know that would be the only place you could use a loop gain. But yeah, non-minimum phase systems are just fine. I mean, I'm sure when Bodhi did his original systems, you know, I know what you're asking. You know, it says in the textbook if it's a non-minimum phase system, like with a right half plane zero in it, it's wrong. And quite honestly, that should be struck from control books. It's just not true. Now, if you have a right half plane pole in it, so the system is open loop unstable, then you get a different situation where, yeah, the Bodhi plot is not going to give you the right answer, or you have to read it differently. But I don't think I've ever seen a power converter come together that naturally has a right half plane pole in it. So you turn up the voltage and this it goes whoop, well, the other way without the controller in place. So I don't think we have that.
Fraser wants to know if we can use this system for inverters.
Inverters are tough because you can only measure a steady state system. So if you've got an AC voltage output, you know, and you're trying to measure the loop gain of that all along the way, then it's just a totally different measurement. So I would recommend that you look at the work by Kai No. who did topics in inverters, rectifiers, and cycloconverters. And he created a rotating frame of reference for inverters and things. If you're building a class D where the inverter is kind of a quasi DC, so you can actually set it at a DC point and measure the loop at all points. So that can be a valid experiment. If you look at the input PFC, the current loop on the PFC can be stable at the top and unstable down the bottom. And the only way to debug that system when you see it oscillating at different points in the loop is you have to set that PFC circuit to DC with a DC input and measure the loop. So yes, sometimes, but the whole class of inverters, they tend to be much slower loops. They tend to be much more predictable. They tend to be, you know, digitally controlled, and they're not doing so much of these loop measurements. But again, every system is a little bit different. Okay. What do we use for the loop gain prediction? Well, we use what everybody should be using, which is Vorpirian's PWM switch model. You crank the equations, and there's that prediction. Okay. So we do not use state space averaging. I haven't used that since 1986, and life has been okay without it. All right, so there we are. We've got our loop measurements, and I could do lots more here. By the way, let's just head back to LT Spice. By the way, we were overdriving this system. Let's turn this into a loop gain from LT Spice. And we add a trace, loop gain. So you see LT Spice here. Actually did an okay job. And then you see distortion here. You see that little bump in the curve there? Okay, and it bumps the phase up sharper than it would, and it just gets all noisy out here because it's just saturating the op amps. So this is a system where we drove it too hard. Is exactly like the hardware. Okay, the LT Spice system is exactly like the hardware. You have to shift the signal size with frequency, and we set that up for you automatically. So if you've got Ridley Works, you just export the model, it sets up the source size. This feature of LT Spice, by the way, of sweeping loops has been there for almost 20 years now. But since LT didn't really believe in sweeping loops much, it didn't really work its way in the software, and they just use a fixed injection all the time, which we know in the lab doesn't work. So what we bring to the LT Spice party here is we know how to set up analyzers, and it's no different in a simulation than it is in the real world. Now, one thing I might expect to happen, by the way, if we imported this loop prediction from LT, it might have a closer Q than the models because it's going to have the ripple on the op amp. Okay, so the things missing from the modeling will be present in the LT Spice simulation, and the simulation will be better than the small signal model. How about that, huh? So you don't expect that normally. Well, it's a simulation, it's not going to be as good, but it actually will include effects that the modeling doesn't include. Any others, John? Are we good?
Oh.
All right, multiple loop crossovers. Yeah, we'll save that. Yes, of course, you have to worry about multiple loop crossovers sometimes. That's getting more advanced. Come to our workshop. We'll talk about multiple loop crossovers. We try to avoid systems like that, but sometimes they can't be avoided. By the way, I love this feature of LT Spice. I've learned so much about setting up analyzers from watching the simulations, you know, just watching these graphics, you know, and of course they generate pretty pictures for you at the same time, which can entertain you in meetings. So, you know, I encourage you to give this a try. It's kind of fun.
So someone, is the model available for these folks?
Is the model?
Is the AP300 model available in piece?
No, and we're never going to do a P-Spice because they're just not interested in working with us on a reasonable level. So if you know how to convert LT Spice to P-Spice, go for it. But no, we tried working with them and it proved to be rather difficult. So that was a waste of time. It's available in PSIM. It's available in LT, and 95% of the world is LT Spice these days. So that's where we're staying focused for now. But I'm sure some of you could figure out how to move it over. But don't underestimate what this takes. You say, okay, well, I don't want to spend any money on getting software. I'm going to write that myself. It's like, okay, but you're talking weeks to get this right. And it took us 2 years to get to our latest iteration that gets variable bandwidth as we sweep and all kinds of things that have really, really cleaned up these plots. So I suggest you ride on our experience there and take what we got there. Don't try to reinvent this wheel. You've got power converters to build. So focus on that. All right, let's move on from loops. I had a lot more experiments on loops, but as always, the task expands to fill the time quicker than I imagine it can. Let's talk about output impedance. With an output impedance, now remember what I said about loops. This is the most important one to do. And when you've got your measurements done, like this, okay, once you've found how to break into that loop and inject the right size, this is the most rugged and easiest measurement to make. Some people think that, well, the loop is the hard thing to do. I don't want to do that. I want to do impedance. I want to do PSRR. Okay, they are much harder to make and get them accurate. Okay, you can do it on a little play converter, a little 5-watt buck converter, sure. Measuring impedance is easy. Okay, we'll do it on this converter, which is 60 watts, but you're going to see it's always noisier. Okay, it's much harder to drive the output impedance properly. Why is that? Okay. So if 20–30% of our industry does loop measurements, I would say about 10% of the industry does output impedance measurements, just because they don't know how to get this going. Somebody asked how much it is to get the AP300 simulator components. Just buy Ridley Box. You've got everything you need with that. It's the demo version is always behind, so spend some money, folks. Free education if you spend some money, so be kind. All right, output impedance test setup. Why is this a hard measurement? Because you've got to take a signal from your frequency response analyzer and you've got to turn it into a current pushed into the output of a power supply. So that's what this does. We isolate and then we push it through this 1 ohm resistor and a coupling cap, because there's a DC voltage there, and you've got to make the output voltage move. And that takes some power to do that. So you've got to push. Okay, so most frequency response analyzers, have a 50 ohm output impedance. We have something of a step down with our isolator. We step it down 2 to 1. So now we've got twice the current capability and we've got lower impedance on this. So it does much better matching and will push more current into the output of the power supply. But still, if you're doing a 100 amp output converter with 100 micro ohms, you're not going to move that output voltage this way. You've got to build a power amplifier to do that, to really push hard on it. So yeah, don't be so eager to say, I don't want to measure the loop too hard. I want to measure output impedance. So it's like, well, that's actually much harder. So beware of that. So let's have a go at that. So let me follow my directions here. I disconnect my loop, or most of it. And then I'm going to get my little handy dandy output impedance tester. Those of you that remember Blue's Clues. Sorry, dating myself. I'm not going to inject there anymore. All right, so I'm going to connect my output of my isolator goes to the test box, which is input from isolator on it. And then channel A of the analyzer goes to the test box. There's a little 1 ohm test resistor in there to give us the signal. And then we take the output of this little test box. Let's go to that previous here. So the output of this test box is going to connect to the output of the power supply right there. And I do it this way on these boards. There's all kinds of ways of doing it. we hook onto the little pins here that we're plugging into the board, like so. And then we connect our probe. We don't hook our probe here up to the injection point, because if we did, we would measure the impedance of the pins, and we'd measure the impedance of the traces. So you're careful to make a 4-terminal connection here. So there's two connections injecting the signal, and then there's 2 other connections measuring the signal. Okay, so this is connected right to the output caps, and this is measured right to the ground plane. Okay, it makes a difference. When people are measuring in our lab, they'll have the probe hooked up to the injection point, and suddenly they've got this 10 milliohms base impedance, which is not correct. Okay, so measuring this output impedance is very sensitive to where you place your probes and your injection points. And again, as the power goes up, the impedances go down. This becomes more and more true. So let's go make a measurement. As you all gathered by now from watching these webinars, I like to run high-risk webinars where I set them up live and I don't quite know what's going to come out each time. So we click on output impedance.
Use this setup to measure output impedance.
Okay, again, it draws you the little diagram, says hello to you. And remember also on the
use this setup to measure output impedance.
You're measuring the output impedance of the power supply, but the load has to be connected. So then some of you will say, well, what if, aren't you measuring the resistance of the load too? It's like, well, yes, of course you are, but if you've built a power converter and its impedance, it better be a lot lower than the load. You know, like orders of magnitude lower than the load impedance, otherwise it's not going to be a very good voltage regulator. So yes, you measure the resistance of the load in parallel, but it's just overruled by the output impedance of the converter itself. All right, so let's see what happens now. Now we see we have a fixed drive. So we're asking this test box here, the Ridley box, for a 4 volts drive all the time. Of course, that's 4 volts, 50 ohms, so there's only so much current drive you can get from it. Let's see if it's going to work. Turn on the power supply. And sweep.
Sweep initiated.
And here you can see our output impedance starting out below minus 60 dB. So minus 60 dB is 1 milliohm. Okay. And you see there's a fair amount of noise here. Phase information, yeah, we don't really care about that. We're gonna try that way. Now it starts to clean up here. Okay, so the impedance is getting higher and we're coupling more current in at that point. So let's go look at comparing to the prediction. Now we click on output impedance. And look at that, it's really good. Okay, you got a really nice sweep versus the prediction here. And this again is in current mode. This bit here is ragged. Okay, can I make it better? Well, I can try. Let's go to the settings. We're doing 100 hertz bandwidth now. And by the way, these comments on bandwidth and source amplitude, they apply to every analyzer out there. Lots of them that kind of fall down on the job to me is that they can't crank up to a decent source amplitude, and they can't turn down to a decent source amplitude, some of them. Sometimes we need to go down 5, 10 millivolts. We can't get there with some of the analyzers on the market, but you know, just contact us if you've got questions. Let's try again. So let's save data set 2. And this is Z out 100 hertz bandwidth. And sweep it again.
Sweep initiated.
And by the way, you'll notice something that we're doing here, which you'll find really useful, is that all the data from the Ridley box just flows into Excel. So you don't need to save a file, put it on a memory stick, any of that stuff. It's just flowing right into your design environment. You know, and Excel's getting pretty popular these days. And that cleans it up there. Oops, bit of noise there. It's not happy about that. But, you know, what can we do? We've got, that's 1 milliohms, so we're down another 10 dB. So we're about 300 microohms multiplied by 50 milliamps. So the fact that it's measuring anything down here is pretty good. This is a tough signal to measure. So now you think, okay, well, we're going to try and use this for predicting loop gain, which I think somebody asked before. Well, the measurement's not very good here. This is just a tough measurement. But you see it's cleaned it up in this region here. Let's make that better. Okay. Any more questions on this? What is the capacitance in the output impedance measurement? In this box, I think it's, remember, it's large. I think it's 56,000 microfarads. Okay, so it's a big cap because you want to couple all the way down to 10 hertz. So you're just trying to make the impedance of that cap low with respect to the 1 ohm resistor and the output impedance of the transformer and the output impedance of the source. Okay, so yeah, if you go back into Ridley Works, we will have cleaned that plot up and it came in a little bit better. So yeah, it constantly updates. Is that the same plot? Or did it update? I hope it updated. No, it does it live. No, the spike is still there, John. So it did update. Oh yeah, it's just the scale. This is plotting to 80 dB and Ridley Works is only plotting to 0 dB. Okay, so yeah, the latest data flows in. And those of you that need to do reports, you know, if you're proficient in Excel, you can do things like cutting and pasting charts into PowerPoint, and they can be live pastes. So you can actually measure frequency response in our Ridley Box or on the AP, and it's live updating in your PowerPoint presentation at the same time. And I could do that too, but you know, there's too many bits of software going on to do that. So that's the story here, and this is, you know, as good as you're going to get out of a high impedance source like this. Okay, it's very difficult to cut through this. And now that's where we go to that's where the AP really shines compared to anything else. So here's the Ridley Box and the AP. Exact same measurements of this. I didn't want to, I've got an AP sitting on my bench here ready to go, but you know, it's too many cables to switch if I do that. But now you can see the AP, because it's got a 2 ohm power amplifier in it, it just cuts right through this noise in here. Okay, so that's the AP measurement in this case. And then we actually compared it to other analyzers as well. And yeah, buyer beware. This is everybody else's analyzer. So this is the AP, and the green one there, we still don't know what happened. That was a Roden Schwartz being used as an analyzer. I have no idea what this is about. And we're using the same test fixtures, the same isolators to make it fair. And then this one here, I'm not going to tell you which one that was, but you know, that just had grounding problems and it couldn't measure anything down below here. So watch out on analyzer. If they're not trying to measure down to a milliohm on a live active circuit, they're not showing you what they're really going to do. Okay, it's not until, you know, you get to these, so you can't compare, you know, these analyzers based on just loop gain. You've got to get into the difficult measurements of, you know, output impedance and the PSRR that's coming along. All right, so if you care about this, you know, that red curve is not good enough, the green curve is horrible, the blue curve is atrocious, that one would tell you there's something wrong with the loop.
Oh, right.
Yeah.
Sorry. Where is the only 100?
Let's just say it's on there, okay? Let's just say it's on there. And to be fair to them, I didn't work on trying to get all the grounds done, but you've got so many things to ground. You got a computer and the box, and you know, it's just hard. These measurements are hard because you're driving power. You're pushing the grounds around all over the place, okay? But out of the box, this is where they all came in on this, okay? And then ours, of course, the Ridley Box it was where it should be, because we took really good care of ground, and we have the computer and the bias supply and the scope all in the same grounded enclosure. Okay, so we get the best results short of running with an AP. Hey, but give it a try. Try it on your power supply. You'll see what you get. Let's go to the next one. Could you do this method with a function generator and a scope like you did many years ago on the freak source? Yeah, you can, but you've got to have some power. So what I did many years ago, I think you might remember, I added an amplifier to it. So I got a vacuum tube amplifier that had about 150 kilohertz bandwidth, and then I could drive some real current in there. And you could do the same thing in here. By the way, you know, you enterprising engineers, this is a nice way to upgrade your stereo for free. You tell your manager you need to measure output impedance well, and you go to the stereo store and you buy a nice audio amplifier, and they have pretty wide bandwidth. They'll put out about 40 volts, and they'll put out 20 amps, and then you can drive the hell out of your kilowatt power supplies. Okay, and then, you know, when it's done, you know, well, it just kind of needs to go home with you at night. You're working from home anyway now. But yeah, I've done that several times. I bought power amplifiers from audio companies just to add more oomph to the test method. Any others, John?
I've heard somebody else says, why don't
Oh, right. Why don't they contain the measurement information to measure the loop? Really good. Okay, let's go there. They do. They do. Okay, so this was our measurement, closed loop of the output impedance. Click on save. All right, we save it. All right. Now we turn off our power supply, and then we open the loop. So you've got to do two measurements, one open loop, one closed loop. Okay, bring it back up again. And we're going to measure it again. Like 50 volts. Okay, back to the box. Let's see if this is going to work. So this is our, let's get rid of data set 1. No, we'll leave that there because we need that one. Sorry, let me clear them all. And then save that data set. This is closed loop. Closed loop. See. Save. All right. Now we're going to sweep it again. So we open the loop.
Sweep initiated.
And now we're measuring the output impedance of a current mode system with the current loop closed. And that's really important. You've got to close the current loop, but you have to make these two measurements in here. Okay, so when the current loop closes, you turn the power supply into a sort of a current source, and all we're going to see is the load resistor right here, and we're going to see the output capacitor. Should have changed my bandwidth there, but we'll go slow. So this is just measuring the value of the load resistor.
Could you have done that just by turning the power supply off?
No, you can't do it just by turning the power supply off, because then, remember, there's two loops in a current mode system. So you close the current loop, then you measure the output impedance, then you close the next loop, and then from those two, we're going to be able to predict what the outer loop gain is. So if I measured it open loop, I'd kind of get the LC filter characteristics, but not really, because the diode would be involved, because it doesn't want to go backwards. So you have to apply power to it to look at the output impedance. You can't, there's nothing useful you can do with just a dead circuit in measuring. When you're in voltage mode control, you could do something there, but when it starts to switch, it's different. Things change. So you two measurements, one just before the regulation point, one just after the regulation point, or in our case, we just get rid of the aggressive loop. We just put in slow components to make this particular measurement. Now I'm still going at low bandwidth here to get a clean trace that you can see there. Okay, so it's sweeping along. Now somebody else can question, could I, oh, that question went away, John, about the impedance?
Yeah, but why?
Right.
I mean, apart from phase information.
Right. If you're listening to some input on this, it is absolutely impossible to tell anything about the stability of power supply with one impedance measurement. It's absolutely impossible. Okay, because you don't know, if you see ringing, you don't know what's ringing. Is it open loop ringing, closed loop ringing? Is it second filter ringing? What is it? So there's nothing you can say about the loop unless you make these two measurements, closed loop, open loop. Okay. So let's stay with that one. Go back to Ridley Works and current loop closed now. Okay, so look at that beautiful agreement there between the green and the purple. The current loop's closed, not the voltage loop yet, and we're plotting the impedance. So you can see it's sweeping into Excel here. Okay, finish it up, I guess. Okay, and then we're going to save open loop. Okay, so I save the open loop data, 2 steps, go look at the loop.
You are using current mode control.
Okay, get rid of the measurement, and then we got this little box here. Once you've made those 2 measurements, you get this option.
Sweep complete.
Calculate the loop from Z out. And there you go, you sort of get it. Okay, and I got to do a phase inversion here, but you sort of get it, but you don't get it here because I can't measure the impedance. All right, but yeah, I see people saying, okay, well, let's measure the loop from the output impedance, but you've got to make 2 measurements. You need a decent power amplifier. So yeah, do this with the AP, absolutely. And you've got to be on the right test points on the circuit, okay? Otherwise, you're just going to get crossover information and thereabouts, but, you know, can it be done? Yeah, and everybody's known this for years. Middlebrook knew this. Output impedance is the open loop divided by 1 plus the loop gain. So you measure the 2, you can back up into the loop gain, but he didn't suggest you do this because the loop gain is such a rugged measurement. Okay? It doesn't have this problem here. Okay, and there's all kinds of other problems. He doesn't have the definition of what's open loop and closed loop. Should I measure unpowered, the current loop closed? You know, where are the test points on the board? I mean, to avoid breaking the loop, if that's the complication, you're making your life actually more difficult. If you absolutely can't break the loop, you know, we've done this a few times for customers that it's like, sure, we'll estimate it for you by using this technique. Okay, but it doesn't really cut it unless it's the only option left. So don't go there because you just can't be bothered to figure out how to break the loop, okay? Because that's your most sensitive health test of the system. All right. Hopefully that answers the question. Let's go to, what's my PowerPoint? There we go. Okay, line injection test setup. Okay, this gets tougher again. This is tougher than output impedance measurement. Other measurement method, 1 quarter shunt through. I mean, just to me, you got to make 2 measurements. I just don't buy these measure 1 impedance and you know stability. I think it's nonsense, quite honestly, but you know. There it is. All right. This is the hardest one to make because you have to break into the input feed to the power converter and you got to disturb that signal. You got to put a signal here. Okay. So buying, you know, I think Chroma makes some, you can put modulation on the power, but you're going to pay a lot of money to do that. So, but you got to break into a high voltage rail or whatever the voltage is. In our case, we got, you know, 60 volts coming in, and we do it this way. It's a little cheap and dirty. It works for up to a certain amount of power level and certain voltage, where you just build kind of an amplifier, which it's a follower, because we want, you know, current driving here to be able to drive this input. So you just go through the isolator from the source, AC coupled to the gate of a FET, and then this FET will have a gate to source voltage dropping across it. And then you can apply modulation to the input of the power supply. So this kind of works. It's a technique we've used for many years. You have to heat sink the FET because it's going to take the full input current across it, and it's going to have a drop across it. All right, and depending on how well you set this up, you know, that could be a significant amount of power that you need to heat sink on here. So, you know, loop is invasive. You know, Output impedance is less so. This is very invasive into your power converter system. I mean, you know, if it's a 400 volt input, you know, you really don't feel like doing this, because this is hard, and it's, you know, can be dangerous if you're breaking that high voltage busing. So let's give that one a go. I know I'm supposed to finish at 12, but we're doing questions at the same time, so it's okay. Oh yeah, by the way, we have an injector to do this, and if anybody knows anything about these injectors, you'll see we achieve something quite interesting here, that the drop from input to output is less than a volt up to about 3 amps, and it's less than 2 volts at 15 amps. Okay, so we can realistically use this for a 10 amp input. Okay, and then if you look at some other line injectors on the market, they just, you know, we chose our FETs and our circuits more judiciously to get this really low drop. And it's all about the power dissipation of this unit. How much heat can you put in here? Okay, so we put all the thermal in there, all the heat sink, and we use the metal case to provide heat sink for us. You can even strap more on there if you like, and run this to even higher current if you wanted to. So that's what we achieve with this. And you can see the blue curve and the green curve. This is different temperature. So at the higher temperature, you get lower gate to source drop in here. All right. So this is a nice way to do it. Again, I wouldn't recommend you try to reinvent this wheel. It's painful. It's a lot of thermal mechanical design as well, but you just don't want to do this. Otherwise, you're going to end up there, and then you're just not going to get the kind of performance that you need. So let's go for the setup here. Right, disconnect my output impedance. Don't need that anymore. We need the line injector right here. Power supply is got, whoops, there goes my T. Denise, you warned me. There's my output of the power supply. There's my plug on the input. Yes, do not have tea and water on your bench. It's a lesson we have to teach all our attendees, but of course we don't pay attention ourselves sometimes. Okay, so that's step one, connecting that to there. Cable. Get in there. Right, input line, and then we have a probe to the output, and the other probe goes to the input. Okay, so power supply rejection ratio now from ground to the input pin. See, we're officially at the end here, but let's measure it first, open loop, since that's what we, that's what we got here. Open loop. Here, turn on the power supply. Okay, so we're going to measure our open loop power supply rejection with the current loop closed. Okay, let's sweep that one.
Sweep initiated.
Oh, sorry, stop. I forgot to click on
Sweep
PSR.
cancelled. Use this test setup to measure input line noise rejection. Sweep initiated.
Okay, so now we're seeing with current mode, we've closed just the current loop so far. And with just a current loop close, you push down the noise rejection almost a factor of 100. Okay, you see it's really low, and we haven't closed the loop yet on this. Okay, so it's very low noise on the output. Okay, so
Sweep complete.
that's current loop closed. Loop closed. Save that one. Now let's look at the open loop. There, so we see where the baseline was before we start. So now we go to voltage mode, but open loop. Turn it on. Measure again.
Sweep initiated.
It should be a clean measurement because it's going to be a much bigger signal. Okay. Oh, we're only using 1 volt here. I'll make sure I change that to 4 before I measure the next one. Okay, so now we're going to see just the gain through the LC filter, and it's multiplied by the duty cycle. That's what that minus 10 dB is. Okay, so now you see it looking like an LC filter. There you go. And then we just get into noise issues out here. There's some sneaky bypass paths that this should be attenuating more, but we're so low on the noise, it's just not able to register it. But look, this is the gain of current mode control. You've gone from minus 10 dB to minus 40 dB just by changing, just by closing the current loop. Here at the resonant frequency, we've gone down 60 dB almost at that point. Okay, so this is what you buy with current mode. So when people don't want to do current mode, it's like, okay, just work a little harder because this is nice to have. At the line frequency, you're just down in the mud at this point. Yeah, somebody else, by open loop, I mean a very slow voltage loop, like a 1 hertz, a 0.5 hertz voltage loop. So that's what that one is. So from 10 hertz on up, there's no loop in there. Right, now we'll do closed loop current mode. And that's up and running. Let's sweep that again.
Sweep initiated.
Did I go? Sorry, I didn't set my source size, did I? Let's go 4 volts. Okay, stop it.
Sweep cancelled.
Make sure we load that setting.
This test set
Okay.
up to measure input line noise rejection.
Sorry, never set it again. 4 volts. Signal. Measure it again.
Sweep initiated.
And then you see we're just down in the mud here. Okay. This is the beauty of current mode. You close the voltage loop, you push it down almost 40 dB. You close the current loop and you push it down another 80 dB from the current loop. So you can't even measure it. And this is why, up to about 10 years ago, everybody gave up on this measurement because everybody was current mode. Okay. And then point of load came along and digital control came along and they couldn't do current mode effectively anymore. So they had to start measuring this because it was so bad in this region. And again, this is just, you know, residual noise transmission that we'd have to clean up all the grounding and everything else. But, you know, we're looking at very, very small signals here. Okay. I mean, these are less than millivolt signals coming out in the midst of, you know, lots more noise. And we'll do one more just for the hell of it. We'll do voltage mode, closed loop, which is that one. Okay, last measurement, I promise, and then we'll deal with all the rest of the questions. Okay, turn on. So we're going to save that as data set 2, closed loop, current mode, save. And one more sweep.
Sweep initiated.
See that difference there between the purple and the blue? Blue, of course, is trying to head down where we can't measure it, but you know, we're looking at 40 dB difference between voltage mode and current mode. And that's just where current mode just wins, hands down. Okay, there's the line frequency again, we're still getting 40 dB there. Okay. Is that a lot of rejection? Well, you know, it depends how much noise is on the input. If you've got 20 volts of noise coming out of your PFC circuit,
Sweep complete.
you know, it's probably going to be okay, but you know, you've got to be somewhat aggressive with the loops to make all this good. Okay, so that third one there, save data set 3, voltage, mode, closed. Again, those of you who said you got an AP, we've got the same interface running on the AP. Okay, of course, it'll clean up these measurements much better. But you can save all these data sets these ways. Everything's in Excel. You know, you can look at the numbers. We just give you the numbers. They're all right there. Okay, so just you know, do what you like. Put them in MathCAD, MATLAB, anything you like. We're just open with all the data here that we give you. Okay, so there's the last measurement on that one. And there you go. One more test setup is the input impedance right here. It's exactly the same as the audio susceptibility, except that you either put a little current transformer here to sense the input current, or you can use a sense resistor. If you can break the ground, you can put a 0.1 ohm resistor to sense it, or a 1 ohm, and feed that into channel A. But the setup is the same, and therefore the difficulty of injecting is the same for this. And you know, this setup is working quite nicely here. We're getting measurements, but the problem is you're trying to modulate this input line, and then you've got the big input cap of the power supply. Okay, so as you go to higher frequencies, it works kind of like a rectifier, and the signal gets smaller and smaller when you're charging caps. So there's a point beyond a certain frequency, and that depends upon your input cap, where this just won't inject very much signal. And at that point, then you need to go to, you know, a different way of doing this, a higher power amplifier, or you need to spend a lot more money on a modulated source on this. Okay, so a couple more questions there. Heatsink inside, well, we take our FET, we mount it on a heat spreader, and then we slap it down to the aluminum case. So the whole case is the heatsink for the system. Okay, so you can probably put 30 watts into this thing before it gets too hot to touch it. So that's how we do the heat sinking there. One porter shunt through measurements. I don't know what all that stuff is with all that, but this is the way we do it in the industry. We've always done it this way for 40 years, and it's not going to change. You know, there's no shortcuts on these measurements with avoiding. I mean, on the loop, you've just got to get in there. If it's a loop and it's breakable, do it. And if it's not, then yeah, you do the best you can with these impedance measurements. Is a 1 megahertz line injector sufficient for most purposes? That's what we have. Ours doesn't go beyond 1 megahertz. You'd have to build a much more sophisticated amplifier to do higher frequencies than that. But you're trying to measure the control frequencies. Okay, beyond that, you know, you're not going to do it this way, but you'd be using something else to do this. You know. So, but this is a way to get the PSRR if you need it without spending too much money on the, you know, the high power sources. I want to turn off that probably now because this one is not heat sunk fully. Blue. What's up?
Flags on these questions.
Okay, what are the flags?
You have to widen your window a bit.
Okay. So yes, there's a heat sink inside the injector. Other methods, I don't know what they're. Sure, there's other methods, but you know, these are the easy ones. 1 megahertz, we got that. Open loop, current loop closed. It's okay. Open loop is, if we go inside our program. Okay, so you've got open loop control to output characteristics. And then you close the current loop and you've got another control to output characteristics. Same with the output impedance. You've got the open loop, okay, which is just the LC filter. Then you close the current loop. That's the first step of the design. Then you close the outer loop. So it's a two-step process. Close current loop, close the next loop. All right, so that's the difference between these three impedances here. Okay. So that looks like we've got everyone covered there, John.
Bernard, his question's there. He doesn't understand what measuring open loop with current loop closed.
Oh, well, you measure the open. No, I don't understand. I don't understand this question. I guess you can measure the control to output with the current loop closed, but if you're measuring the loop gain with the current loop closed, you're measuring the loop gain. So send me an email if you have more on that question. All right, so there we go. A bit late here, sorry. Always takes me longer than I thought. There are lots of experiments I skipped. I do encourage you all to, give this frequency response in LT Spice a try. If you can't measure stuff in the lab, measure it in LT Spice. But find a way to go in the lab, get a signal generator, get a scope that can measure this and look at these quantities, okay? And the big deal, of course, about a frequency response analyzer is if you're just using a scope, you've got all the noise. And you can't get rid of the noise easily and see the signal. Okay, so that's what a frequency response analyzer will do for you. And some of the scopes now will let you put adjustable filters on them. But this is part of your toolkit for the future. These techniques are not going to go away. They'll be here for the entirety of your career. Everybody will be measuring these quantities. So I just encourage you, go learn how to do it. You've probably got 30 different network analyzers out there. Okay, avoid some of them because they're just play kits basically. They're Digilent. You buy this box for $300 and you got 50 wires to hook up. So you have to build your own frequency response analyzer. So we did that. We got a measurement and then we put 5 volts on it instead of 3.3, and we didn't have a Digilent anymore. So that's not so good. Analytic Arts, we had trouble with that one too. They just don't have protection, the ruggedness, and everything that you put in. A production piece of machinery. So, just spend your time wisely on that. All would be good, but learn the skill. Students, go out there and learn the skill. How does Middlebrook criteria apply? Yes, we'll get back to that one. Again, I want to do a webinar that talks about the undamped input filter, the Middlebrook criteria, and then how we can redesign the system and apparently violate the Middlebrook criteria, because that's becoming very important in high efficiency systems. Because efficiencies go up to 99% for some of these converters, you can't afford to damp the filter anymore. So if we can compensate the system without damping the filter, wouldn't that be cool? We can do that. Again, that was APEC last year that got canceled, so we'll do that again. Those of you that want to learn from us, we have a live version of this where we ship you all this equipment and you do all this yourself. And it's far more involving and engaging than we hoped it would be. It's really good. So we have 10, 12 people in the room at a time. Everybody's got a test set up. They're going to make all these measurement lives. You're going to wind transformers and inductors, and while you're stuck at home, you can get this training yourself. And I think we're booked. March is booked, April is fully booked, and we just added May on the list. So, and we're not really advertising it at this point. Everybody just finds out when's the next one, and we just tell people to watch out and sign up, and we send them an email. So that's the next course date is May 17th through 21st. And we've actually expanded our 4-day workshop to 5. And that it's just to reduce the pressure on everybody in the course. There's so much that we do in our workshop, and there's so many topics to cover. I can't stay to the schedule here in 2 hours. So you can imagine with a 4-day, it's just too much. So we've added a 5th day to relax the design process, and sign up for that if you can. UK version of the workshop right now, we have quite a few customers of the Ridley Box in Europe, and the initial Europe workshop will be for people that already have one, because the problem right now during this whole COVID thing and the turmoil in Europe is shipping expensive gear in and out is tricky. And, it's going to take a while for that to sort itself out. So if you already have, getting it into your country is easy. Getting it back out again is when it gets difficult, and obviously we don't want to lose things. if the pandemic is over, we will be back to England sometime, hopefully in the fall. Looking at my two traveling companions here.
Q4.
Q4? Yeah. Well, we'll go for Christmas, right? Maybe we'll have a UK workshop in Christmas. You know, just before Christmas or Q4. Okay. Yeah, when everybody's vaccinated and everybody's safe to move around. Ray, I'm using every bit of your workshop at work now. Fantastic. Thanks, Jorge. Like to hear that. Is APEC going to happen this year? We're supposed to find out today, I think, is when APEC is going to make their announcement, but we're not going. I'm not going anywhere. Not till the world is vaccinated. So how much RAM to add to current mode conversation, how to couple it? Get our software, it adds the ramp for you, no problem. It's all calculated internal to the software. And I think our demo software even does that too. So there's the workshop. Other things, if you want to try RidleyWorks, send us an email. We can send you the full demo. You can give that a try. If you want the best resource for conversations, interaction with 5,000 engineers, come and join our Facebook group, okay? I know you may not like Facebook, but it's okay. Just come in there for the group because we've got 5,000 engineers and there are great conversations going on there. I learned so much about so many things that, you know, I really encourage you to come and join that. If you want to see more webinars, and you can click on these links, by the way, in your PDF document, you know, there's a whole bunch of these webinars now. This is number 11 of the series, and we'll do more. And we may also consider different types of formats for teaching, something between our full course and, you know, this free version. So we may have some, you know, longer training sessions with some, you know, entry fee to get in there that we teach, you know, like the Middlebrook one, I think should be like that, where we really get into depth and we send you test software so you can step through it with us, but a real teaching environment for, you know, half a day or a day. So we're looking forward to that too. Are we going to put the video on LinkedIn? No, you have to come to our design center to find it. So just go to our design center. That's the webinar series, okay? And they're all on YouTube ultimately. So you go to the design center, you click on it, you can download the PDF, and then you can watch the videos from the past. But one thing we've noticed, they're always better live. Everybody stays really engaged. We've still got 210 people in the room here, which is pretty amazing. When you watch it as recorded, for some reason it's not quite as exciting, but the information is there. So there's some really good stuff, I think, on our webinars from the past. If you need a frequency response analyzer, you got this one here, which is the top of the line. Anybody in aerospace, you know, this is what you should have for the full aerospace calibration. This one here is great for everybody that's doing other work, and you've seen it in full view now. And of course, the Ridley Box is actually running the entire webinar, running all these pieces of software and making measurements. And yesterday we had it running the AP at the same time. Everything was running at the same time. So we put a pretty powerful computer in there. And yeah, RidleyWorks is part of the Ridley Box. It's a lifetime license for RidleyWorks in there. So it's an entire design center. And with our customers right now, we have, you know, we have a port into, so they will send us the password. We actually go in and we update the software for them. If they're having trouble with measurements, we come in and then we help them debug their measurement. So that's been really nice because the whole software environment is what we placed there. So we actually link in and suddenly you've got us in your lab to help you out with all of this. There's Facebook group, Design Center articles, webinar series, and current mode. Somebody's asking about current mode. Here you go, get the free book. Then you don't have to get the software, but you'll spend, you know, 2 months reading the book rather than 5 minutes reading the software. So it's up to you. And then of course there's the Ridley Box, of course, to look through. So if we don't have any more questions, I appreciate the kind comments from you all. Trevor Smith, hi Trevor, good to see you. We'll be talking tomorrow. Glad you came. And there you go. I think we're going to sign off at this point, and everybody have a great day. And we'll see you again in probably 4 or 5 weeks when we do another one of these. Thanks so much. Okay. How do I end it, John? Wow. Exit. Take care, everybody.